So this is 9.9 slash 9.10, which is lengths of curves and surface area. Okay, so when we're talking about the length of a curve, right? So we're talking about if we happen to have, say here's a curve in space, and I'm interested in between this point, so we'll say that's A, and this point here, so some value B. I want to know how long that curve is, right? So if you think about, back in pre-calc 1, we could find the distance between 2 points, but the distance between 2 points would be the straight line distance. Here we're talking about the distance on that curve. And so, in this case, I'm trying to think, no, I finished, all of a sudden it dawned on me that I don't know. Yeah, I did I finished. All of a sudden I was like, wait, did I finish section 6.3? Everything's running together here today. Sorry about that. Okay, so I did. Back to lengths of curves. So we're talking about, we found in Math 126 the straight line distance, if I made a straight line between those 2 points I have. But this time I'm talking about if I wanted to figure out how long the curve is. And so there's a formula to do that. The formula is that the length is equal to the integral from A to B of the square root of 1 plus dy dx squared, all integrated with respect to x. So it's kind of a combination of basically essentially what you're doing is you're breaking this curve up into an infinite number of little tiny line segments. And if you think about it on a little tiny little line segment, like if I think about it like kind of like right here, right? If I were to draw the tangent line, the part of the curve, like the tangent line for a second, is really close to how the curve is. And remember, the tangent line talks about how the function is changing. So that's why there's a derivative inside this formula for the length. Questions? Okay, so let's do some examples then. So for example, actually, my example is probably longer than this. So let me go to another page. Oops. So, for example, find the length of the graph y equals the natural log of the cosine of x from x equals 0 to x equals pi over 4. Right. So remember that formula I just put up there was that the length is equal to the integral from a to b of the square root of 1 plus dy dx squared dx. So I have the curve. I know where I'm going from, right? So it's just a simple matter of plugging in here. So RA is 0, RB is pi over 4, square root of 1 plus, okay, so we have to find the derivative of the natural log of the cosine of x. So how am I going to find the derivative of that? Okay, so the derivative of cosine x is minus sine x, yes. But what do I have to do first since it's the natural log of the cosine of x? So you don't need you need the absolute value if you were integrating, not if you were taking the derivative. So remember, if I have, okay, so yeah, so remember, if you have the natural log of a bunch of stuff, right, and I'm taking the derivative of it, remember that's equal to 1 over the stuff times the derivative of the stuff, right? Stuff prime. I know it's kind of squished in there. So we have to do 1 over cosine x. So 1 over cosine x. So 1 over the stuff. Now times the derivative of the stuff. So times minus sine x. And then that's all squared dx. Yeah, and so that actually is exactly what we want to do. So we have 1 over cosine times minus sine x. Remember, sine over cosine is tangent, so we actually do want to rewrite this from 0 to pi over 4 of, the square root of 1 plus minus tangent x quantity squared. And if I square the minus tangent x, it's really just tangent x squared, right? So we have the square root of 1 plus tangent squared x dx. Anybody remember what 1 plus tangent squared x is? Yeah, it's secant squared x. So we've got the integral from 0 to pi over 4, square root of secant squared x dx. I'll come over here. And so if I take the square root of something squared, I just get that something, right? So this is going to be 0 to pi over 4 secant x dx. And then secant x is one of the ones I have on that sheet, right? So the integral of secant x is the natural log of the absolute value of secant x plus tangent x, evaluated from 0 to pi over 4. So we're going to have the natural log absolute value of secant of pi over 4 plus tangent of pi over 4 minus the natural log absolute value of secant of 0 plus tangent of 0. And then we just have to figure out what each of those are, right? So we've got the natural log. The secant of pi over 4 is root 2. The tangent of pi over 4 is 1. So the absolute value of root 2 plus 1 minus the natural log absolute value. Secant of 0 is 1. Tangent of 0 is 0. So this whole second term is just the natural log of 1. And remember, the natural log of 1 is 0. So my final answer is that it is the natural log of the absolute value of root 2 plus 1. Questions? No? It's not too bad compared to what we've been doing, right? It's kind of just plug and chug into the formula. Are very questionless today. It's kind of odd, right? Usually there's a little bit more, you know. Okay, should we try another one? It kind of depends the hard part. So it kind of depends on what you think is the hard part. I would say that the majority of people think that series and sequences is the hard part. And so we have not done those yet. That's actually what we're going to start next class. I don't think they're that hard, but. All right. So let's try another one here. All right, so then we're going to look at surface area. So surface area. So the formula for surface area we're going to use in S is going to be 2 pi times the integral from a to b of r of x times the square root of 1 plus f prime of x squared dx. And where r of x is the distance between the graph and the axis of rotation. So when we're talking about surface area, we're back to talking about three-dimensional shapes that we're revolving. So a two-dimensional shape that then we're revolving around, right? So surface area is something that is only found on three-dimensional shapes, right? Regular area is what's found on two-dimensional shapes. So, for example, find the surface area formed by revolving f of x equals x cubed from x equals 0 to x equals 1 about the x-axis. So we'll draw a picture here. Remember, y equals x cubed looks like this, right? But we're only talking about the part from 0 to 1. So say here's 1. So we're talking about this area there. And we're going to revolve that around the x-axis. So we would make that mirror image and revolve that around. So r of x is basically the radius, just like we were doing in the disc and the washer method. So r of x is that exact same thing. So in our case, our surface area is going to be 2 pi. Our integral is going to go from 0 to 1. And then r of x, right? So if you think about putting in here, if I put in that radius here, right? That radius is sitting on the curve. So r of x is x cubed. And then we have the square root of 1 plus, okay, we need the derivative of our function. So our function is x cubed. So what's the derivative of x cubed? Yeah, 3x squared dx. So we're looking at 2 pi times the integral from 0 to 1 of x cubed times the square root of 1 plus 9x to the 4th dx. And so I just have to integrate that. So how am I going to integrate that? Yeah, do a u substitution. So if we let u be equal to 1 plus 9x to the 4th, du is going to be 36x cubed dx. So I have the x cubed. I need a 36 inside here, which means I need a 36 outside here. And we'll change the limits too, just to make our lives a little easier. So we used to have x equals 0. So u is going to be 1 plus 9 times 0 to the 4th. So that's just going to be 1. And then we had x equals 1. So u is going to be 1 plus 9 times 1 to the 4th. And so that's going to be 1 plus 9, which is 10. So 2 over 36 is the same as, so half of 36 is 18, so pi over 18. So pi over 18 the integral from 1 to 10 of the square root of u du, or pi over 18, the integral from 1 to 10, u to the 1/2 du. So that's going to be pi over 18. What's the integral of u to the 1/2? Yeah, 2/3 u to the 3/2. So 2/3 u to the 3/2, evaluated from 1 to 10. All right, so the 18 and the 2 would cancel, give me a 9, 9 times 3, so I've got pi over 27, u to the 3/2, evaluated from 1 to 10. So pi over 27 times, if I put 10 in, can't really figure out what that is, right? It's 10 to the 3/2. And then if I put 1 in, I'm just going to get a 1, right? So minus 1. And you can leave your final answer like that. Questions? No. Does anybody need me to wait to go to another page to do another one? No problem. Yeah, let me know when you're ready. Okay. So let's try another one here. So find the surface area of the solid formed by rotating f of x equals x squared from 0 to the square root of 2 about the y-axis. Okay, so again here, right, I have, here's my curve. So we're rotating the part from 0 to 2, right? Or 0 to square root of 2. And I probably should have said I want the part that's inside here. I should have made that a little clearer. Formed by rotating that about the y-axis. So we're talking about making a solid this way. So we're interested in finding the surface area of that. So the surface area is going to be 2 pi times the integral from 0 to root 2. So in this case, our radius, right, it starts in here and it goes out to the function. So it's going out, it's stopping at the function, but my radius is in what direction? No, the 0 to square root of 2 still applies to the x-axis. I didn't word it great. So I should have said by rotating like this function, the part of this function that's between the function and the y-axis. I should have been clearer about that. Aiden. I didn't make it super clear. Yeah, so it's at the bottom is the x squared. Yeah. Okay, so Sandra said that, yeah, my radii are all little parts of the x-axis, right? So the radius here is just x. It's saying I'm going out some distance x. It's moving, right? So the radius is x, and then we have the square root of 1 plus, so what's the derivative of x squared? (2x), so 2x squared dx. So we're talking about 2 pi, the integral from 0 to square root of 2x, square root 1 plus 4x squared dx. And again, how am I going to integrate this? Okay, so remember, inverse tangent is like, you could use trig substitution to do this. Trig substitution is a little bit of an overkill, but it would be a tangent in the trig substitution. So we're just going to use u substitution. So yeah, u would be 1 plus 4x squared. So du would be 8x dx. So I need the 8 in front and a 1/8 out side here to balance it. And then again, I'm going to change the limits. So when x is 0, u is going to be 1 plus 4 times 0 squared. So it's just going to be 1. And when x is root 2, u is going to be 1 plus 4 times root 2 squared. So root 2 squared is 2. 4 times 2 is 8. 8 plus 1 is 9. So we're going from 1 to 9. So we've got pi over 4, the integral from 1 to 9 of u to the 1/2 du. I just rewrote the square root as the 1/2 power to begin with. So just like before, I've got pi over 4. The integral becomes 2/3. 2/3 u to the 3/2 power, evaluated from 1 to 9. So we end up with pi over 4 times, or I guess we could actually make that a little nicer, right? The 2 would cancel with the 4, so pi over 6 times 9 to the 3/2 power, minus 1 to the 3/2 power. So 9 to the 3/2 power, so that's going to be, you're going to take the square root of 9, so square root of 9 is 3, and then 3 cubed is 27. So I've got pi over 6 times 27 minus, this is just 1, so we've got pi over 6 times 26. Right, and I could cancel some of those. So 2 goes into 6 3 times. 2 goes into 26 13 times. So 13 pi over 3. Questions? So the problems aren't too bad, right? The surface area problems I actually think are a little bit nicer here. But again, we're going to talk about surface area again later on in the course. So we're not going to like spend a bunch of time talking about it right now. Yeah, so that's a good question. So So it's because it is on the function. So you're right that we're going out into the function. However, x squared is referring to the y distance and not the x distance, right? If x squared would be giving this distance, these blue distances, that would be giving the distance up to x squared. So we're not doing that distance, we're doing the horizontal distance. That's why it's just x. No problem. Other questions? Does anybody need me to wait before I go on to the next page? Okay. All right. So, what we're going to do now is actually one of like my kind of favorite calc problems. And so it's called Gabriel's horn. And so, it's called Gabriel's horn after, in the Renaissance, they had the painters painted like angels and all that kind of stuff, right? So the angel Gabriel has a horn, and so that's why they kind of name it Gabriel's horn. So Gabriel's horn deals with the function 1 over x. And so it takes the function 1 over x, and we start at 1. So we're taking the function 1 over x, starting here at 1, and we're going to rotate it about the x-axis. So I'm going to get this mirror image. Now the thing is it doesn't ever give, it's not saying the part between 1 and like say 7 or 1 and 10. It's starting at 1 and it's going forever. So it's this infinite surface, this infinite picture. So, here's that original part, which is the 1 over x, and then we're rotating it, and so you can kind of see it looks like a horn type like shape, right? Kind of like those long trumpet type shapes. Okay, so we're going to find the volume of Gabriel's horn, so using stuff like we did last time, and then we're also going to find the surface area of Gabriel's horn, right? So the volume. So if I was going to find the volume of this object right here, what method would I use? Would I use washers? Would I use discs? Would I use shells? Like which one? Yeah, so it's a solid disc. So using discs are good. So the volume here is going to be pi times the integral. So we'll worry about the limits here in a minute. So remember, it's the radius squared. So what is the radius of my discs? If I stick a disc in here, right, where is the radius sitting? So the radius at the beginning, at the beginning it's 1, but then as I move inward and I look at all these different discs, the radius keeps getting smaller, but the radius is always sitting on what curve? 1 over x. So it's going to be 1 over x squared dx. And then I'm taking all those discs, I'm starting at 1, but I'm going all the way up to infinity, right? It's going on forever. So this is going to be, this is kind of ties in stuff from the second test. So this is really just a limit problem. So it's the limit as b approaches infinity of pi times the integral from 1 to b. And I'm going to write this as x to the minus 2 dx. And so if we integrate x to the minus 2, we would just get x to the minus 1. So the limit as b approaches infinity of pi x to the minus 1 over minus 1 evaluated from 1 to b. Or the limit as b approaches infinity. I'm just going to rewrite this to make it look a little cleaner. So really we have minus pi over x evaluated from 1 to b. So if I plug in b, I have the limit as b approaches infinity of minus pi over b minus negative pi over 1. And so if I plug in infinity, right, I've got minus pi over infinity plus pi. And so this first part here, right, goes to 0. So the volume turns out to be pi. Yeah, so it's very interesting. So you have this shape that goes on forever, but it actually has finite volume, right? So that's kind of weird. So that's one of the cool things about Gabriel's horn. The second thing we're going to find about Gabriel's horn is we're going to find the surface area, right? So the surface area is going to be 2 pi times the integral, again, it's going to be from 1 to infinity. So the radius here, right, is the same as the radius we just did. So it's 1 over x times the square root of 1 plus, so remember we're trying to take the derivative of 1 over x, right? So the derivative of 1 over x is going to be, so I have x to the negative 1, so it's going to be minus x to the minus 2 squared dx. Does that make sense? Questions? Okay, so remember, we're taking the derivative of 1 over x, and 1 over x is x to the negative 1. So it's going to be negative x, and then remember for the derivative, you subtract 1 from the power. So negative 1 minus 1 would be negative 2, and then we're squaring that. Does that help? I just want to make sure I answered your question before I go on. No, it's just the derivative. My function here is f of x equals 1 over x, right? And I can just rewrite that as x to the negative 1. I didn't take a derivative there. I just rewrote it. So then when you go to take the derivative of that, right, you get minus x to the minus 2. Other questions? No. Okay. So this becomes 2 pi, the integral from 1 to infinity of 1 over x square root of 1 plus 1 over x to the 4th dx. And the problem becomes this is an integral that we don't know how to integrate. None of the techniques that we know to use would work on this integral. So this is not really one that we can do by hand. What we can do, though, is I do know how to do this integral. I do know how to do this integral. So we know the following. We know how to find the integral from 1 to infinity of 1 over x dx. Right? And we know that the integral we were given is going to be bigger than this, right? This integral here, we can figure out what this is, and then I know that this integral here is going to be bigger than it. And you might be like, how do you know that? Well, I know that because it has a 1 over x, and then it's 1 over x times something, and this something is bigger than 1. It may be really close to 1, but it's still slightly bigger than 1. So this function here is bigger than 1 over x, so then when I take the integral, it's going to be bigger. So if I look at this first integral, or this new integral here, right? This is going to be the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. And what did we say the integral of 1 over x is? Yeah, natural log, absolute value of x, evaluated from 1 to b. So we're going to have the limit as b approaches infinity of the natural log of b minus the natural log of 1. Natural log of 1 is going to go to 0. Right? So when I plug in infinity, we're going to have the natural log of infinity. So infinity is a giant number. Remember, the natural log grows forever. So this whole entire thing just becomes infinity. Right? So it's not the integral I was looking for, but it's an integral that goes to infinity. It just blows up, right? And the integral we were looking for, the integral of 1 to infinity of 1 over x, square root of 1 plus 1 over x to the 4th dx, is bigger than the integral from 1 to infinity of 1 over x dx. Which means, since this integral went to infinity, this one's got to be bigger, so it's also got to go to infinity. So it's also got to diverge. Okay, so you might go, okay, fine. Why is this so cool? Why did Dr. Gorman get so excited when she stuck up this Gabriel's horn, right? So this means that you have a finite volume, right? So the volume of the Gabriel's horn is finite. It's a number, but we have an infinite surface area. Okay, so that's just weird, right? Finite volume and infinite surface area. And if you're kind of like, okay, I guess it's weird, think of it this way. If that horn was hollow, it's saying I could fill that horn with paint, right? That's what having a finite volume means. You could fill the horn with paint, but there's not enough paint inside the horn to paint the outside of the horn. That's weird. It's crazy weird, right? Yeah, so how is it? It's because the function gets so close to the x-axis that it's not really adding any more volume as it goes out, but when it's rotating around, it's still adding significant surface area. So that's like why it happens, right? So as it gets smaller and smaller, the horn gets tinier and tinier, right? It gets pretty tight where you can't fit any more volume in, but there's still a little bit of the surface area, and that little bit of surface area keeps adding up. So that's how come you end up with infinite surface area but finite volume. So it's just a cool problem, right? I feel like it's one of the first cool math, like paradox type problems that you can see, right? There's not many of them that, a lot of times to get to these weird mathematical paradox type things, you need a lot of stuff. But for this one, you don't, right? You just need a little bit of calculus. Pi can keep going. Everybody knows Sunday's Pi Day too, right? March 14th, right? Yeah. Questions? No. Yeah, Sunday is the time change too. Yep. So it's a time change and it's a Pi Day. I know. We can't have giant Pi Day celebrations. It's kind of sad. Right? When we're in a classroom, I usually bring my class pie on Pi Day. But no pie this year. Cal can be fun, right? My husband was originally going to propose to me on Pi Day. So he was pretty nerdy. He wanted to propose to me on Pi Day at 1:59 p.m., right? Because the first couple digits of pi are 3.14159. But I already knew he had the ring and I was antsy, so he proposed the day before Valentine's Day. But yeah, it would have been a good story if he had actually proposed to me on Pi Day, right? Yeah, he's nerdy too, right? He's a math person too. So, okay, so I know it's not even 3:00, right? And this like never happens. But that actually is all I wanted to cover today. So you guys lucked out, and you can have a nice rest of your afternoon. If anyone has any questions, you can feel free to hang around and ask. Otherwise, I will see you on Tuesday, and on Tuesday we're going to start series and sequences. Also, I should say too, before I forget, there's not homework on these sections up, and I'm not putting homework on these sections up right now. We'll have homework on surface area and arc length later on when we revisit it again and we do the parameterized versions. So it was kind of like a for your enjoyment type lecture today, which I'm sure you guys are like, this is not how I would pick a for my enjoyment type thing. No, so actually, volumes and like I'm going to put up, I'm going to give you guys that project, and I just didn't have it written for today, so I'll have it written for Monday. And by project, I mean, it's like a small type thing. It's not actually like a regular project. And so it's basically like kind of like a slightly more involved homework problem, I should say. So it's not something that's like massive, going to take you a long time. But I do that instead of actually putting it on the test. So their volumes and stuff will not be on the test. The next test will just be on series and sequences. Yeah, so the stuff that's due this week is the stuff from last class. So it's basically all the volume stuff. So there's a section, and those are all up already. So there's a section called 9.3, and then there's a section called 9.3 part 2. So it's those two things. So it's basically discs, volumes by discs, washers, and shells. That's what's due for homework. No problem. Have a good rest of your day.